You know, when you think about someone like Einstein, it's kind of mind-blowing. How did he come up with these world-changing ideas? Basically just by using his imagination. Well, today we're going to deconstruct exactly that. We're diving into the amazing world of thought experiments, these powerful tools for discovery that don't need a lab, just your mind. And let's start with the original term, because it just sounds so important, right? Gedanken experiment. It's German, and it translates literally to thought experiment. And this isn't some new idea. It's been a secret weapon for philosophers and scientists for centuries. So what is it, really? A thought experiment is basically a tool of pure reason. It's a way to take an idea, a hypothesis, and really test it out by imagining a situation and then following that situation to its logical end. All of it happens right here, in your head, without touching a single thing. Okay, but that brings up a huge question, doesn't it? If you're not actually doing anything in the real world, how do you know you can trust the results? I mean, what's the difference between a groundbreaking thought experiment and just a really convincing story? Well, there's an answer, and it all comes down to a few very specific rules. The first rule, and honestly the most important one, is that a good thought experiment can't just be some wild fantasy. It has to be connected to the world we actually live in. It needs an anchor to reality. Our source material uses a great word for this connection: a trace. You can almost picture it like footprints in the sand, leading from your big idea all the way back to the solid ground of the real world. No matter how creative your scenario gets, its parts have to be traceable to something real. And this right here is such a key distinction. An idea can be perfectly logical, totally rational in its own little world, but if it doesn't have that trace back to reality, it's just not realistic. And that gap between rational and realistic, that's everything. For instance, let's take this classic idea from geometry. In the pure, clean world of math on a flat piece of paper, this statement is 100% rational. It's a perfect truth within that system. But what happens when we take that perfect, rational idea and try to apply it to our messy, three-dimensional world? Does that trace to reality actually hold up? And here's where it breaks down. In the real world, the shortest way to walk from one mountain peak to another is obviously not a straight line burrowing through the earth. That perfectly rational 2D idea falls apart when you trace it to our 3D reality, with its hills and valleys. A valid thought experiment has to respect these real-world limits. Okay, let's move on to rule number 2. So, we've got our idea anchored in the real world. Now we have to make sure the thinking process itself is solid. And here's a fantastic way to think about it. A thought experiment is like running a simulation on a supercomputer. You plug in your starting variables, which, remember, are anchored to reality, and then you just let the program run. The only difference is the supercomputer is your brain. And what is the absolute number one rule of any good simulation? It has to be logically consistent. You can't just change the rules of physics halfway through, right? Every single step has to follow from the one before it, with zero contradictions. This is so important. If that chain of logic breaks at any point, the whole thing is a bust. One tiny inconsistency, one little bug in the code, and the whole thought experiment comes crashing down. The conclusion just doesn't count. So we've got an anchor to reality, and we've got rock-solid internal logic. But there's one more layer here. We have to look at the kind of foundation the whole experiment is built on. Yeah, it turns out not all starting points are created equal. You can build a thought experiment on what's called a limited projection, which is based on truths that are only true in a specific context. Or you can build it on a universal projection, which is based on truths that hold up everywhere. So that shortest distance is a straight line example. That's a perfect example of a limited projection. It's based on the relative truth of a flat 2D plane. It works perfectly there, but it doesn't scale up to the real world of mountains. The conclusions you can draw from it are super narrow. A universal projection, though, now that's the gold standard. This is when your thought experiment is anchored to something absolute, something like a fundamental law of physics. When you start from a foundation that's truly universal, your reasoning can be both flexible and rigorous, and it leads to conclusions that are powerful and consistent pretty much everywhere. Okay, let's bring all these pieces together. What have we learned? Well, a thought experiment is definitely not just daydreaming. It's a disciplined, structured tool for discovery. So the next time you come across a thought experiment, you can actually run it through this little test. First, check the anchor. Are its starting points traceable to the real world? Second, check for consistency. Does the logic hold up all the way through? And third, check its foundation. Is it built on a limited idea or a truly universal one? At the end of the day, our imagination is an incredible laboratory. It lets us explore ideas and possibilities that we could never physically test. But for those explorations to be legitimate, for them to actually lead us to truth, they have to follow these very strict rules. And this leaves us with one last really big idea to think about. I mean, it's pretty incredible that our minds can actually model the universe just by using pure logic. So if our imagination has to be anchored to reality and logically consistent to find truth, what does that tell us about the deep, fundamental connection between the way we think and the way reality itself is structured? It's a pretty wild thought.
Welcome back. Today we're taking on a word that we usually think of as total disorder, chaos. But what if I told you that inside the most famous scientific model of chaos, there's a hidden structure, a beautiful, unbreakable, and perfectly predictable order? It sounds impossible, right? Well, let's get into it.
Okay, we have to start with the question that made this whole idea famous. You've heard it a million times. Could a tiny butterfly flapping its wings in Brazil really trigger a massive tornado over in Texas? This is the core of what we call the butterfly effect.
Now, this isn't just some cool philosophical idea to think about. It actually comes from a very specific place, a mathematical model designed to simulate the weather, known as the Lorentz system. It's all rooted in real math.
Remember how we talked about the fact that any good reasoning needs a trace back to reality? No matter how wild our ideas get, they have to be connected to the real world somehow to be meaningful. Without that trace, an idea might be perfectly rational, but it's not necessarily realistic. So that brings us to the big puzzle here. What happens when our reasoning, our math, seems to tell us that reality itself is fundamentally unpredictable? Where's the trace to follow and the path forward looks like pure chaos?
To get to the bottom of this, let's treat it like a detective story. First, we need to look at all the evidence for the myth, the strong case for why this system seems like total, unpredictable chaos. So, back in the 1960s, a meteorologist named Edward Lorenz was running these early computer simulations of weather, and he stumbled onto something mind-blowing. He found that a tiny, almost unnoticeable difference in the starting numbers he put into the simulation
would lead to a completely different result down the line. We're talking about a change smaller than a rounding error, like 0.0001%, creating a sunny day instead of a massive storm. It makes the whole thing feel totally random and unfair.
And, this is what most people think of as chaos theory, a system so sensitive that trying to predict its future is basically impossible. It feels like proof that the universe just has some fundamental randomness built right in.
But hold on. This is the big plot twist in our detective story. The evidence isn't quite what it appears to be. So now, let's look at the reality, the hidden, and I mean really hidden, case for absolute order.
Here's the amazing part. The biggest piece of evidence against true chaos is the Lorentz formula itself. Why? Because the formula is perfectly consistent. It follows its own rules 100% of the time without ever making a mistake. It is not random, not even a little bit. And this table just lays it out perfectly. In practice, our perception is that the system is random and flawed. But the reality of the formula is that it is totally consistent and predictive. If you give it the exact same inputs, you will get the exact same output every single time.
So what does this mean? It means the chaos isn't in the math. It's in the real world. The problem isn't the formula. The problem is that we can't measure every single starting condition with perfect, infinite precision. The logic of the system is flawless. It's our ability to measure that has limits.
So, if there's this secret order hiding in there, can we actually see it? Oh, absolutely. And it's stunning. Let's get to the visual proof and see this hidden symmetry for ourselves.
So, imagine you run these Lorentz equations thousands of times. Each time you start with a number that's just a tiny bit different from the last one. Every single outcome, every path it takes, is going to be unique. No two are ever exactly the same.
But here's where the magic happens. When you map all of those thousands of unique paths together, they don't just fly off in random directions. Instead, every single one is pulled toward a very specific and beautiful shape. This is the famous Lorentz attractor. It looks like a butterfly's wings. This right here is the smoking gun.
This is the deep, unbreakable symmetry hiding inside what looks like chaos. No matter how random any single journey seems, it is always guided by this elegant underlying structure. It's proved that there's a profound order holding it all together. So, what we've discovered here forces us to rethink what we even mean by the word chaos. What we're looking at isn't a breakdown of the rules. It's a system with an incredible level of intricacy. We need to shift our thinking from chaos to complexity.
So let's give ourselves a better definition. In this context, chaos is a relative term. It doesn't mean true randomness. What it really means is that we've hit the limit of our own perception. We've reached the boundary of what we can measure in a system that's just super complex and sensitive.
So let's just sum it all up real quick. First, the Lorenz system itself is not random at all. Its math is deterministic. Second, the chaos we see is really just our own inability to measure everything perfectly at the start. And finally, and this is the most important part, it's a limit of our perception, not a failure of logic in the universe. And that leaves us with one last big idea to chew on. What other things in our world that we call random, like the stock market, or even how languages evolve over time, what if they actually have a deep, hidden pattern that we just don't have the tools to see yet?